table. Let us go for the voltage measurement. So initial resistance measurement, current measurement is done. So mainly electrical or electronics deals with the four things. So there is resistance, there is current, there is voltage, and there is power. These are the four things mainly we can ask in network analysis for any circuit. Okay, if it is a DC circuit. For AC circuit, again there will come power factor, there will come some active power, reactive power, all those things. For DC series circuit, only four things. That is equivalent resistance, current, voltage, and power. Okay. So resistance and current is done, and this is the sequence. First we find resistance, then find current, then find voltage, and then find power. Okay, and we are going in the sequence. Resistance is found, then current is found. Now we are going to find what is the voltage across each individual resistor. So connect the voltmeter in parallel. So two things already we have shown, that is internal resistance of voltage source ideally is 0. Internal resistance of ammeter ideally is 0. Now we are going to see what is the internal resistance of a voltmeter. So voltmeter internal resistance ideally is infinity ohm. That you have to remember. And voltmeter has to be connected in parallel to connect the voltage. What is meant by voltmeter connected in parallel? This is the parallel connection of a voltmeter. So V1 is the voltage across resistance R1, and this way you can connect a voltmeter across the resistance across which you want to measure power. And why I am showing a dashed line here? Because these are temporary connection. So just connect the voltmeter, can remove it from R1 and connect the voltmeters across R2. Again remove the voltmeter and connect the voltmeter across R3. So whenever you are connecting, whenever you are removing, no parameter in the circuit is changing. Okay, that's why those voltmeter are called as temporary connection. That's why voltmeter connections are shown by dashed lines. But if you check the previous circuits, if you check this circuit where I have connected the ammeter, this ammeter connections are shown by solid lines. This ammeter connections are shown by solid lines, because if you remove ammeter from here, there is no current flowing in the circuit. So ammeter connections are permanent connections, but voltmeter connections are temporary connections. That's why if you need to measure 2-3 different currents in the circuit, in that case it becomes difficult for you, because 2-3 different ammeters in that case you need to make a stable connection in the circuit. Otherwise you have to just keep on removing the points, insert the ammeter, measure the current, again remove the ammeter, join that point, again go to the other point, make it open, connect ammeter. Likewise, an unstable kind of a measurement you have to do. So what I mean to say is, ammeter in the circuit is a stable circuit. Okay, if you remove this ammeter, the whole circuit gone. The circuit is not going to carry any current. But if you are talking about voltmeter, in that case the voltages are actually a parallel connection. The voltmeter has to be connected in parallel. If you remove this from R1 connecting to R2, then again you are getting V2, again removing across R2 connecting it to R3, and you are calculating, finding what is V3. So voltmeters are connected in parallel with the resistors. They may be removed from one point and connected to the other, hence they are shown by dashed lines. So these are very formal way of showing the circuit components and circuit notations and direction of voltmeter. So which direction is positive, whichever is the current entering junction. So this is a clockwise current direction in the circuit, hence always current is flowing from left to right through all the resistances. That means for all the resistances, left side is at higher potential and right side is at lower potential for all the resistances. So left side is at higher potential, right side is at lower potential. Hence, whenever you are connecting a voltmeter, the left side red probe should be left side and black probe should be at the right side. And if you are doing reverse, if you are doing black in the left and red in the right, you are going to get a negative voltage reading. Okay. So whenever you are measuring voltage, red probe should be there in the left side and black probe should be there in the right side, because the current is entering the resistor from left side and current is leaving the resistor through right side. So there is no standard rule. Whichever direction is a higher potential in the circuit, that you have to understand, and that point should be connected with the red probe and the other point should be connected with the black probe, and resistor should be connected in parallel. So conclusion is voltmeters must not be connected in series. So you cannot just break open between R1 and R2 and connect voltmeter. Not possible. Voltmeters are not to be connected in series with the resistor for voltage measurement. But unlike ammeter, so if you are connecting ammeter in parallel, ammeter will burn because its internal resistance is zero. But if you are connecting voltmeter in series, it will not burn because voltmeter internal resistance is infinity. As soon as you are connecting voltmeter in series with the components, you will find that circuit current will drop to zero. Because if you by mistake by connecting voltmeter in series, internal resistance of voltmeter is infinity, and this in current flowing through infinity will tend to zero. So voltmeter must not be connected in series with the resistor for voltage measurement. It has to be connected in parallel for voltage measurement in parallel with the resistor. It will not damage the voltmeter if you are connecting voltmeter in series. Measurement of voltage if you are connecting the voltmeter in series with some resistor. So there's a conclusion. What next? Theoretical voltage calculation. So now onwards, everything I have shown theoretical calculation. That means taking the resistance values as 1000, 470 and 100. Practical things you can do during experimentation when you come here in the lab. But voltage calculation, power calculation, all I have done by using the theoretical value of resistances. So initially we had found I in as 5.09 milliampere. So how much is the voltage across R1? So voltage is equal to resistance into current. So voltage V1, that is voltage across resistance R1, 5.09 into 1000, 5.09 volt. Same thing across R2, 5.09 into 470, 2.39. Be very careful about this milli. Okay, you are not careful enough about this milli and all, and you make big mistake in this voltage calculation. So be very careful about milli. Milli means 10 raised to minus 3. And V3 is nothing but voltage across resistance 3. So current is 5.09 milliampere multiplied by this resistance. Ideal value is 100 ohm. So this is 0.509. So just check one thing. This R1 and R3, they are having resistance ratios of 1000 as to 100. That is 10 as to 1. Okay, I'm not considering R2, but R1 and R3, their 5.09 and V3 is 10 times less than that. So that's why this circuit is called as voltage divider, and the voltage gets divided in the ratio of the resistances. So even if you don't calculate IN, just take this value 8 and divide it in the ratio of 1000 as to 470 as to 100, and this will be the answer. So without calculating, without finding out IN, just by applying mathematical ratio division, you can find out what can be the distribution of voltage across all these three resistances. And by electrical method, we first find IN, multiply by resistor and find what are the voltages. Finally, add all these three voltages and you will be finding V1 plus V2 plus V3 will be equal to 8 volt. So whatever is the supply voltage given, that same voltage is absorbed in different loads across the circuit. Okay, so that is actually KVL. Practical voltage calculation, do it yourself, because in that case R1 will be 990, R2 will be 455, R3 will be 108. This should be actually 104. I'm sorry to the correction. So in that case, IN is 5.16 milliampere, and with 5.16, V in practical will be 5.16 milliampere multiplied by 990. V2 will be 5.16 milliampere multiplied by 455. V3 will be 5.16 milliampere multiplied by 104, and accordingly all these voltages. And as per KVL, all these voltages, if you add in case of practical, that should be equal to the 8 volt whichever is given here. So KVL can be proved for theoretical calculation as well as for practical voltage calculation. So you can do it yourself when you are here, or you can assume some values of practical values of resistances and you can prove KVL. So for an increased value of IN, then also the KVL will be proved very perfectly. So there will be no problem in that. This is a very important thing. How to find power in the circuit? Okay, so all calculations are done with theoretical values of R1, R2, R3, that is 1000, 470 and 100. So students have to repeat the same calculations for practical values, that is 990, 455 and 104. For same parameter, they have to assume the practical values of resistor within plus minus 5% of tolerance band. Power input. So with theoretical values I have calculated. So how much is the input power to the circuit? So input voltage is 8 volt. There is no doubt in that because we are setting it from the DC power supply source, and I in theoretical that we have found as 5.09 milliampere with 1000 ohm, 470 ohm and 100 ohm. Okay. So P in is equal to V in multiplied by I in. So whatever current goes through the circuit, that is input current. So voltage multiplied by current is equal to power, and we are finding it to be 0.04072 watts or 40.72 milliwatt. This much power has gone inside the circuit. So whatever voltage you are giving, this R1, R2, R3, they are actually drawing this much power 40.72 from the 8 volt supply. Okay, so whatever is the source power or whatever is the given power to the circuit is actually a P in 40.72 milliwatt. So there is one formula, P in is equal to V in into I in theoretical. This is one way of calculating input power. There is another way of calculating input power, that is I in theoretical square multiplied by R in theoretical. Okay, or R equivalent or R theoretical equivalent. So P in is equal to I in theoretical, that is 5.09 milliampere square multiplied by 1570. That was the equivalent resistance when all three resistances are connected in series. Okay, so that is 1570 multiplied by 5.09 square. Okay, so that will be giving you 40.675 milliwatt. So it is the same thing. Okay, so almost 40.675, 40.72, they are almost the same thing. Okay, because this is in milli, so not much difference. So either you go by V in into I in, or you go by I in square into R equivalent. Okay, so that is going to give you the same power. Any method will do. Hence, source power to the circuit P in is equal to 40.675 milliwatts. So I'm taking this value, which is calculated by I square into R equivalent. Okay, so power source is V in, current is 5.09 milliampere. Total power given to the circuit is 40.675 milliwatt. Now, when this much power is given to the circuit, this makes the current flow through the resistors. Resistors dissipates. Dissipates means eats power. Okay, it just uses the power. See, this mobile phone that you are using, it is having both the modes. It is having the power sinking mode when it is charged, and it is having the power sourcing mode when you are using the mobile phone. Okay, so power sinking means power is going inside the battery. So in that case, the direction of current will be towards the V in. And what is power sourcing? Power sourcing means current going out from the positive end of the battery. Okay. So when this much power, whatever is given to the circuit, it makes the current flow through the resistor. Resistor dissipates this power with formula of I square R. And resistor gets heated up because they do some work. So resistors are the sink or they are actually dissipated power. Resistor are the sink for the input power. So whatever power is the input power, whatever power is given, resistor is sinking that power. That means eating that power. Source power is used for utilized at resistors. Resistors are the components where power is dissipated. Dissipated means utilized, used. So they are dissipated in the term of heat or something. Initially, what we have found is input power is 40.675 milliwatt. Power dissipated by all resistors R1, R2, R3 is given by this formula. The power dissipated by R1, that is, there is a current flowing through R1 square into resistor, 25.90 milliwatt. This is the dissipated power at R1. Dissipated power at R2, 5.09 milliampere square multiplied by resistor values 470 like this. Dissipated power at R3, 5.09 milliampere square multiplied by 100, 2.59. What is the total dissipated power in the circuit? That's equal to PR1, PR2 and PR3. Total, if you are doing, it is coming to be 40.66 milliwatt. And this red is the dissipated power, and the other thing, this P in, it was 40.675. So first we have calculated in the previous slide what is the input power V in into I in. Then in the next slide what we are finding is how much is the dissipated power total, that is PR1, PR2 and PR3. That comes to be total 40.66, and we just check in the lab. Okay, and with actual or practical values also you have to calculate all this power and add them, and that should be equal to something, and that we will measure with the actual theoretically calculated power. And there will be minute deviation, it cannot be exactly correct, okay, because it's a lot of squaring and other thing, errors are coming because there is a lot of truncation and you are approximating it, so it should not be exactly equal. So if it is 40.675, it should be 40.68, or it may be 40.8 milliwatt, that is also okay, but it should not be 42 milliwatt, that is not there. Okay, so how much is the tolerance, that we know, we can tell you. So you just show your result to us and we say fine, whatever practically dissipated power you are getting, that is almost same as theoretically calculated input power. So in that case the power law of the circuit is satisfied. What is the power law? That is source power should be equal to sink power. So for resistive circuit it is easier to prove that source power is equal to sink power, but as you keep on growing, keep on going to the higher classes, you'll be finding circuits with dependent source. Dependent source means this is an independent source, it is 8 volt means it is 8 volt. Okay, so as you go in the deeper things in NA, higher other modules, you will be finding there is coming a concept of dependent source. Okay, so with dependent source also it will be a little difficult for you to prove this source power is equal to sink power this easily. It also can be proved, but it cannot be proved that easily. So circuits with dependent source with semiconductor material, it will not be this easy to prove it. Okay, but for every circuit this law is obeyed. So whatever power you are giving, that much power is dissipated, because if you are dissipating something means it has actually come inside. Okay, otherwise how could you dissipate? So every time, for every circuit, at least as long as you are in DC resistive circuit, for every circuit try to prove this power law, that is how much power is given to the circuit and how much power is dissipated by the resistive component in the circuit. Finally, I'll show you this observation table. So here this observation table for all the theoretical values of resistor. So this kind of table, first you have to complete, and then you can go to your table and perform these experiments. So this is the first experiment I have done. So V input I have taken as 8 volt. Just now I have shown all the calculations. R1 1000 ohm, R2 470, R3 100. R equivalent, so I'll write it in a more neat fashion and I'll post this PPT to you in PDF form. So R equivalent is addition of all these three. So there's a calculation level, everything is theoretical. There is no measurement, error by ohm meter. Okay, next table is for that. So next table, this is for practical value. So in this case 1000 ohm will not be 1000 ohm, because resistance values in that case will be measured. So this will be 990, this will be 455 and this will be 104. Okay, so both these tables I will be showing you, just a representative table I will show you and I'll upload it to you. Okay, so first, what is the input? 8 volt. You can take any cases, not necessarily you have to take these values, but only resistor values you have to take standard values. Just don't take 239.7 ohm, don't take that. Okay, there are standard resistance values, you just take that. And R equivalent is addition of all these three. Okay, so 1570, and what is the I equivalent? That is 8 divided by 1570, that is 5.09 milliampere. Then for every resistance I have found equivalent voltage, for every resistance I have found equivalent power. So for one row I have done the calculation and I have shown you. For other rows you can do the calculation and you can show it very easily. So 6 volt and this resistance values I have taken, not necessarily you have to take 6 volt and this values. You can take any voltage and any standard resistor values. For third case 9 volt and these are the resistor values I have taken, and you can just fill up the tables. So we will be giving you only this much, you have to just fill up the whole table and then you have to go to the table to perform the experiment, and there all this table you have to fill up with all the measured values and all the measured practical readings you have to fill it. So actually these resistance values I have given wrong. This should be the measured values of this theoretical resistance values, and they will always be showing some kind of deviation because of tolerance in the component. So I will be changing this tables, and I'll be making it much better and send you the whole slide to you, and the video of this 2 hour session I'll be uploading it in YouTube, and I'll be sending it to you. If you are having any doubt, you can post it in the group, and what to write, how to write, in due time we will be giving you that instruction. And this is only the part A of this experiment 1. Part B will be parallel circuit. So series circuit is over, DC supply and parallel resistive circuit will be there, and all this cautions, all this notes, all these cases that we have shown here, how to connect voltmeter, how to connect ammeter, how to connect the ohm meter, that means loop open, loop close, connect series, connect parallel, all these fundamentals will be used throughout this NA lab for all the experiments. So please remember that. So next day onwards we will be only sticking to the basic calculation and practical related calculation only, with all this basic assumptions and basic rules set for your lab. That's all from me. Any doubt, you can post in the group. You can write to me, or in your third semester group, if you are posting doubt, we will be answering your doubts.